I would like to introduce Raymond Hettinger, the ETA Tools guy, who will be talking to us about the art of subclassing.
Hello, everybody. I'd like to show off some code I've been working on for 9 months and just put into production 24 days ago. This is Matthew and my lovely wife, Rachel. And this is his first appearance at a Pycon. All right, let's begin with the art of subclassing, which is going to be an interesting talk to give because I'm followed by Jack Diedrich, who will tell you to stop writing classes at all. So this is kind of interesting progress this morning. Meta classes to subclassing to no classes at all, and I just don't know where that trend will continue to. It'll converge on a singularity. So where we're headed today is almost everybody in this room certainly has written classes before, has an idea of what subclasses are, and so I'm going to ask you to humor me through the first part where we go back to the very basics and show you things that you learned a long time ago, but with the idea of picking it apart and see if we can rebuild our notion of what a subclass is. I know everybody in here has written subclasses before and has seen a few patterns, and we'll definitely give you more of those and show you some Pythonic ways to do it. But one of my goals today is to reformulate your idea in your mind, to expand your mind a little bit, to cause you to think about it in a slightly different way. Almost certainly everything you've already been taught is true. Almost certainly everything that you've already been taught handcuffs you and causes you to think more limited thoughts. So my goal is to free your mind, Neo, and hopefully you'll swallow the red pill. So we'll revisit the notion of what a class and subclass is. We'll talk about some of the use cases and design patterns. One of my favorite topics, super, we'll only be able to touch on for a few minutes. I have this belief that Python super has a superpower that other languages don't have, and it's very different from other languages. And then sometimes when I say something that sounds incredulous and just unbelievable, no one in their right mind would ever do that. So I try to give examples from the standard library, and people say, this code is evil. So the person who wrote this should be shot. And then we'll bring Guido in, and you guys can shoot him. And so I try to use some authoritative references, and when I talk about these things, I don't like to use ABC diagrams. I like to get into something that's concrete. You guys ready to rock and roll? You willing to swallow the red pill and give up your long clung to notions of, this is how you have to do subclassing in Java? Okay. All right. This is a profound example of code. Please, my apologies for giving you this piece of code. This is a class animal. It has a docstring, generic animal class. It has an initializer, and it has a method called walk. Walk uses new style formatting. Are you impressed? Okay. But we're not here to talk about animal. Can you hear? Okay. Does that mean I need to talk louder, or somebody needs to change the volume knob? Can you hear me now? Ooh, I've got a little reverb. That's awesome. Okay. So I specialize the animal class with dog, and I extend it adding a method. Are you guys very impressed with my code? All right. Who learned something new? I hope not. My goal is to show you what you've already learned, and then we'll go unlearn it. And we'll also learn all the terminology associated with it. The terminology is adding. Dog adds the bark method to animal, which didn't have a bark method. It's a new capability. Overriding means that I can replace an existing method in the subclass. So a snake subclass replaces walk with a walk method that knows how to slither instead of walk. Extending is taking the existing walk method, taking advantage of the walk that's already there, but then adding on an additional capability. So we use the inherited capability of walking, plus we add some behavior so that a cat walks and swishes its tail at the same time. You guys love these profound animal examples? All right, good. I appreciate the humoring me part. We will ramp it up a notch. So let's talk about some of the patterns of subclassing for a moment. The framework pattern, this is an official name for it. It's in the design patterns book by the Gang of Four. And the idea is all the control logic is up at the top in the parent class. And then the subclass comes along and adds or overrides a handful of specific methods in order to make the class more concrete or customize it to a particular use. So in our HTTP server, all the logic for doing the server is in the simple HTTP server class. How many of you used this simple HTTP server class? Okay. How many of you are ready to move on to more modern tools? Okay. Okay. But for our purposes here, it's not whether this is a great class or not. It's a classic. What's interesting is how you use it. You don't instantiate this class directly. You subclass it. And then the methods that are provided inside do get and do head, the methods that are called when you get a head request or a get request. The parent calls those methods, and they are stubs. And the definition of them in the standard library is do get is pass, and do head is pass. So if you'd like your server to actually do anything with the request, you subclass it and define these two. So this is a classic framework pattern. I'd ask who's learned something new, but everybody in here has used this class, it sounds like, and so that is the framework pattern for subclassing. It's an old classic. It's also very static. What are our choices for methods to override? They've been defined in advance. You can do get, do head, do put, and do post. There's no way to add other methods to this capability because the framework drives everything, and it tells you in advance, here are the handful of methods you can subclass. It's not a very flexible pattern. Dynamic dispatch is much more flexible. Who's ever used cmd.py? Okay, not enough of you. All of you should put it into your toolkit. How do we spend our days? We write these big bags full of functions. We write modules and packages, and we write hundreds of functions. And how do they get used? Someone fires up Python, they import your package, and they start calling them because they know the Python syntax. Wouldn't it be nice to make it usable by someone who is not a Python expert? CMD makes it very easy to take all that work that you did for a week, and in 1 minute, you can have a front end for it that has a command shell. And then within a half an hour afterwards, you can expose all of your commands with a nice help function, the ability to scroll back to old commands for somebody who doesn't know a Python syntax. So I put an example of that in the Python 3 docs. And even if you're not a Python 3 user, it's worthwhile to go check out the documentation for it because I put in a front end for the turtle module. This turtle module is wonderful. It's a great way to introduce kids to programming. The problem is they have to immediately learn Python syntax. They have to learn how we do our for loops and while loops and defs and whatnot. So I put a front end on it, and the front end took about half an hour to 45 minutes to build. I subclassed from command.py, and then anytime the kid types forward, it will call the do forward command and set up the argument pattern appropriately. How does that work? The way it works is inside the cmd.py file. This is an excerpt from that file. You guys are reading the source code for the standard library, right? I contend that the best way to become a better Python programmer is to spend some time reading the source code written by great Python programmers. I don't know who wrote this one, but it's a quality piece of programming. There's lots of good pieces of programming in the standard library, and reading some snippets of code will make you a better programmer. So this snippet says, if a user types in a command like forward, which comes in as a string, and it's pre-parsed so that the argument is separated out, so they put forward space 10, forward will come in as command, and 10 will come in as an argument. What this will do is a get attr on self. It will look up into the current class for a method called do_forward, meaning the way you use this in a subclass is you make a subclass of cmd.py, and you add a method do_pin down. Now whenever the user types pin down, the get attr will figure out that the method should be called do pin down, look down, find this method, and call it for you. And so this is a pattern of subclassing that's a lot more flexible than the traditional framework pattern, and it allows the subclasser to have a great deal of control and to add one command after another without changing the parent class. I think it's a lot better way to go. I almost never use the framework pattern anymore. I always use a dynamic dispatch. One of the themes of this presentation will be, as the writer of a class, what a lot of people do is once they get the class working, tested, and documented, you quit because you think you're done. But the next step after that is to polish it and think about subclassers and try and make life easier for the people who come after you. And that person might be yourself. And I'm going to show you the principles of making your subclasses easy to use. And one of them is dynamic dispatch, making it to where a subclasser can add a method of do_pin down, and they don't have to go change the dispatch logic. Fair enough? Who learned something new? All right, a couple people. More is coming. All right. The call patterns for a subclassing. I've got a circle class here with it defines a radius, has a a method that computes its area in a nice repr. The part we're interested in is the subclass. The subclass calls the parent class as init by referring to it directly using the name circle. That is kind of an old style. We can also use super to do the same thing. And we'll talk about super a little bit later. So this is an extending of the init method because we use the parent's init method, but we add on some extra capabilities. We say, let the parent do the parent thing, but then add the new donut capability of storing the inner radius for the donut. In this case, we override area rather than extend it. And when we override area, this completely replaces the area up above and says, now let's take our outer and inner radius to compute the two areas and take the difference of them. So we're demonstrating in here, one is extending, two overriding. But what's interesting is a call pattern. When I instantiate donut and I go to print it and get a repr of the donut, the search pattern is it starts from the bottom, the instance of donut, it looks first in the donut class and says, does it have a repr? If not, it goes up to the circle class and says, does it have a repr? Going up to the parent. So its repr starts to run. So circle's repr is running on donut. Then it says it has an area. This is an interesting pattern that is frequently used in Python. Rather than hardwiring the name, circle has an area of so-and-so. I've made life easier on the subclasser by not referencing my class name specifically. So I didn't hardwire circle here. So this is a very common pattern. You'll see it used throughout the standard library. We say, take self, whatever the instance is, ask what class it is, and you're like, when you're just writing circle, a person who wrote circle and wasn't thinking about donut would be very tempted to hardwire the name here because they weren't thinking about subclassers. What I'm trying to do is get you to the point where you think about your subclassers saying, you know what, self, we need to stop thinking of self as being you. Self, whoever wrote circle was thinking of self as a circle, but self could be one of your children too. So self is actually an instance of donut and not an instance of circle. And this theme will come back to us over and over again. We need to get back to really break our mind free of thinking that self has any relationship to circle. It is one of your ancestors, our descendants. So that's an instance of donut, so that gets the donut name, drops it in. And then it computes self.area. Now this one's interesting. Self.area, is that the circle area? The writer of this class might have expected that self.area would call this area. But it doesn't. It starts with self at the bottom, and self is an instance of donut. It works its way back up and finds this area. So we find this bouncing pattern. It goes like this. We got a donut. The donut needs a repr. Goes up to a donut, doesn't find it. Goes up to circle, finds it. Circle starts back with self, asks self its class and its name. And then it goes to self.area at the bottom, working its way back up. And so you get this bouncing up and down. So the patterns of subclassing are always at any point where you refer to self, you go all the way to the bottom and start working your way back up again, leading to some interesting things like the person writing this code very much expected that self.area was this area instead of this area. But this class was designed in a way that was very flexible and made it easy to subclass. So at this point, I don't have a whole lot of teaching principles other than say, this is a very common pattern. You should get in the habit of using this. And we're trying to free your mind by saying, don't think of self as a instance of the class that you're writing. This is of particular importance when we start talking about super. And I will cut to the chase real quick or reach into the future and talk for a moment about super. The number one misunderstanding of super is in every other language, when you call super, it means I'm calling one or more of my parents, either my father, Ray, or mother, Gail. That's how it works in other languages. What does it do in Python? The hint is what's happening here with self.class name. It starts at the bottom. Self might not be you. So I have a method where I call super. Who's going to get called, my father or my mother? It turns out possibly someone unrelated to me because I have a descendant, Matthew. And so Matthew, my descendant, might have been the one to call me. And when I call super, it is not my ancestry tree that matters, it's his ancestry tree. And when I was created, my dad didn't know about Dennis or Sharon or Rachel, but Matthew knows about them. So when Matthew calls me and I call my super, I call someone in his inheritance tree, not mine. So potentially, when I call super, it will not be my father or my mother. It might be Matthew's mother or one of Matthew's other grandparents on the maternal side. Does that make sense? So super doesn't mean go up. Super means go up from your children Always start at the bottom, work your way up. I'm going to ask who learned something new, and I'm expecting every hand to go up. Okay. Super can call somebody that is not in your ancestry tree. It is the subclasser that is in control. It is Matthew that controls where super is going to go. It is not me or Rachel. Okay. So let's retool our thinking about subclasses. We're going to just go back to the basics, and at this time we're going to break apart the notions of that very first class I showed you, the animal and the dog, and say let's think about them in a different way. I'm going to compare and contrast how you were taught versus how you should think of things in Python. And how you were taught was not necessarily wrong. It was applicable to a lot of circumstances, and in some other languages they will be patterns of thought that will be the only successful patterns of thought. If you were a Java programmer or a C++ programmer, there are patterns of thought that are useful to you that cause you to code correctly in those languages. If you then bring them over to those thoughts over into Python, they will cause you to think in a way that is very constrained. We call them bondage and discipline languages. Instead, we want to free your mind and let you think of them in a much more broad way. So, what does it mean to be an object or class? The classic definition is an object is an entity that encapsulates data together with functions called methods for manipulating that data. So you brought the data together with a set of functions for manipulating it. This is the primitive notion of a abstract data class. How do we implement that in Python? Because it's implemented differently in different languages. Operationally, we implement it with dictionaries. So instance dictionaries hold the state. That's the data, and they point to their class. And so the class dictionaries hold the functions. So I like to, in my advanced class, show classes always demonstrated as a pile of dictionaries as opposed to classes and instances. And the reason is if you start thinking about them as dictionaries, you start thinking in a more flexible way. So in this diagram, you've got 3 instances of a class. In the class dictionary, what's in it? A bunch of functions for manipulating the data that is in these instances. Each instance has its own data. Data on the left, functions on the right. I'm going to ask who learned something new, and I'm expecting very few hands. It's necessary for us to bridge off of this definition and to propel us into the future, so thank you for humoring me. By the way, notice the direction of the arrow here. A lot of times you'll see class diagrams written with the arrows in the other direction. Why does the arrow go this way? The instance dictionary has a pointer to the class dictionary. The instance dictionary says, I have this data, and here's a class that's full of functions, a dictionary of functions that knows how to operate on the data. The instance points at the class, not the other way around. The direction of the arrows is important. It's a hint to how we should be thinking about the classes. So, if we know what a class is, what's a subclass? It's just another class that delegates work to another class. A subclass and its parent are both dictionaries or functions, and so a subclass points to its parent. So Matthew points to me, I point to my father and to my mother. So we have our 3 instances which contain the data. They point to a dictionary that contains a bunch of functions for manipulating on the data, and then the subclass dictionary points to another dictionary that has functions for manipulating the data. Note the direction of the arrows. The children point to the parents. It's a hint. The pointer means the translation of the pointer is not the traditional translation that you were given. What do people tell you it means to subclass? When you're first being taught about subclassing, you're told to subclass is to specialize. That's not in this definition. What does the pointer mean? The pointer means I delegate work. This is, the instance dictionary says, I have a piece of data. I'm pointing to some functions that I'm delegating to do some work on that data for me. The subclass says, you know what, I don't want to do all that work myself. I've got somebody else to do the job for me. This is the subcontractor. It's the parent is the subcontractor, not the contractor. The instance says, subclass, I want you to do all of the work. Subclass says, I'm going to look like I'm doing all of the work. I'm going to farm it out to another class and works its way up. From the point of view of the instance, all of the work is being done by the subclass and not by the parent. Okay? So I'm trying to expand your mind slowly here by saying the direction of the arrows goes up, and the meaning of the pointer is I'm delegating work to somebody else, work that I was supposed to do. Okay, so what does it mean to be a subclass? Subclassing can just be viewed as a technique for code reuse. And that's starting to get us into a mode that is normative, that tells us how we should be thinking about our problems. It will be the solution to some of the problems coming up. You know, how do I think about the answer to this problem? How do I design my class? this is the hint of what the answer to that question is going to be. The other interesting hint of what's coming up is who's in charge? The person with the pointer is in charge. In my house, the dad had the car keys. He was in charge. Now I have the car keys. Guess who's in charge? The person with the pointer is the one in charge. The instance is in charge of who does any work at all. The subclass is responsible for some doing work. It can delegate it to someone else. It has all the power, which is not the way you were taught. The subclass decides which work gets delegated. So let's contrast our two views, the traditional definitions versus, is that 15 left?
15 to Q&A.
We may not get to Q&A. Okay, so we will contrast the two views of subclassing. So the operational view is a class, and operational means the implementation. It's just a pile of classes are dictionary functions. Subclasses point to other dictionaries of functions so they can reuse their code, and subclasses control what happens. I'm going to say this should be the dominant view. The traditional view, the conceptual view that you were taught, the bondage and discipline point of view, the point of view that has chained your mind to the matrix is at the bottom. Parents define an interface. How many of you were taught that the parent class defines an interface? Okay, you came from a bondage and discipline language. Subclasses can extend that interface. The parents are in charge. At my house, my dad decides when the garage gets cleaned. He doesn't have a garage cleaning capability. I extended that. He calls my garage cleaning capability all the time. The parents are in charge. So subclasses can extend the interface with garage cleaning, but the parents are in charge. All subclasses are a specialization of parent. You were taught that, and we've given you many confirming examples. For example, we know that dog is an instance of animal that knows how to bark. It's a specialization of animal. A counter is an instance of a dictionary that knows how to default to 0. A name tuple is a tuple that has an extended capability of attribute access. It's just a specialized tuple. A counter is a specialized dictionary. A dog is a specialized animal. This is how you were taught. It is not wrong. It is a useful style of thinking. Unfortunately, it leaves your mind in the matrix. To get out of the matrix, you shift from this point of view at the bottom to this point of view at the top. All it is a pile of dictionaries. Guess who's really in charge? It's not the parents, it's the children. What things can go in classes? Any functions you want. What does it mean for something to subclass from another class? When I subclass from something, I'm saying I'm taking work I was responsible for and handing it to somebody else to do that work. I've decided who I subcontracted to. Okay. So with that little bit of freeing the mind, I'm going to let that just kind of sink in for a moment, and we'll talk about the Liskov substitution principle for a moment. The idea of Liskov substitution principle, this is the official statement of it at the top of the way Barbara Liskov stated it back in late 70s or early 80s. The idea is this function at the top was written with animals in mind. Animals need to have a name. So I'm expecting that if this code works with animal, that it will also work with a specialization of animal, a dog. A dog should be perfectly substitutable here. Since an animal has a name, a dog has to have a name too. The Liskov substitution principle says you have only designed your classes well if they obey this principle of the subclass is substitutable for the parent class. So now you have a new technical term in your hip pocket, and you can go around telling people you have a Liskov violation. Off to the Russian front. Okay, so why do we care about Liskov? It's all about polymorphism and substitutability, which are fine things. It allows us to take our subclass and stick it and use it anywhere the parent class was used. I took good advantage of this with ordered dictionaries. Ordered dictionaries subclass from dict. They didn't have to subclass from dict. I could have made them standalone. Why did I subclass from dict? I did it so that they were immediately usable in the huge amount of Python code that's been written. Pretty much anything that expected a regular dictionary, you could stick an ordered dictionary in instead, which was fantastic. I immediately had a giant set of clients already pre-written for me the moment ordered dict was deployed. Liskov substitutability was a fine thing. It's something that we strive for. Here's the traditional examples with a cash register and credit cards. You accept a payment type of some sort. You specialize that payment into cash or a credit or check. And how do you accept a check? You see if there are persons on a list of people who don't write hot checks. How do you accept a credit card? You call the credit card company and they authenticate. How do you accept cash? You check to decide whether you have enough change involved or not. And what's nice about that is it lets us write a huge amount of cash register code and then later decide to add a new credit card type. And I'm going to specialize credit cards, so I have a different procedure for Amex versus Visa or MasterCard. And so I put new ones in, and I don't have to change any of the client code, any of the giant code base for the cash register. That's the big win that comes from list-off. So you should strive in the design of your classes, subclasses to have list-off substitutability. So it is list-off substitution what? Fill in the blank. List-off substitution principle, not list-off substitution law. Substitutability is a big win. Lots of code in Python works with dictionaries. Ordered dict is a dictionary. Accordingly, I can use it everywhere else. However, you can violate list-off. Any part of an API of the API that isn't fully substitutable is a list-off violation. Is this okay? Don't feel guilty. This is common and normal. You can tell your parents about it, just don't tell your friends. Okay, all right. So list-off violations are very common and normal. So we have lots of things in Python that are list-like, but one of them is array. Who's used the array module? So array module gives you some space efficiency that lists don't have. So you have a list of 10 million floating point numbers. You can store them with no overhead and an array object. Array objects are fully substitutable for list in every way except for one, which is the constructor. The constructor takes a data type, F. So there might be a piece of code that calls self.class in the name of the iterable that goes with it, and that piece of code would be broken by the list-off substitutability here. It is okay. Subclasses typically have different constructor signatures, which is, the more you violate list-off, the more you lose substitutability, but sometimes you have to. Our goal is to take cases where the signature is different and try and minimize the impact, because the more you minimize the impact, the more you increase substitutability. So the constructor for list is we pass in some iterable. For array, we pass in a data type, C for character, and some iterable. These two are not substitutable because they have different constructor signatures. Fair enough? All right. In some cases, like arrays, that's not that big of a deal because it's not too common for arrays to go duplicating themselves using this way. There's other ways like using slicing that work just fine. But sometimes it matters. An example was with sets. What is the basic business of sets? It is doing set operations like intersect, union, difference, whatnot. Who's used sets? You like them? Awesome. So you do the difference of two sets. What does it produce? A new set. How do you produce a new set? You have to call a set constructor, which is a real problem if your subclass has a different signature. So in the abstract base class for a mutable set that allows you to define new sets, we have provided for you the code for union, intersection, difference, and whatnot, and all you have to do is provide a constructor. The problem is your constructor might not look like our constructor. Ours takes an iterable. Set consumes an iterable and produces a new set. What if yours takes a data type? Would you be able to use mutable set at all? The answer is we factored out that difference into a method called underscore from iterable. Every time we need to create a new set, we don't call the constructor directly. Instead, we call underscore from iterable. This was Guido's idea. I keep saying we because I get credit for some of his big ideas. So Guido factored this out into from iterable, which the idea is every time union or difference needs to come together and make a new class, it calls from iterable, and from iterable calls the constructor. Meaning if your constructor has a different signature, all you have to do is override one method from iterable. And a way to do that is to take the first element of the iterable, compute the type of it, make a type set. You override from iterable, make your own initializer, and inherit from mutable set. And now you've gotten for free union, intersection, difference, whatnot, which I think is fantastic. You learned something new in API design for subclassing. Factor out all your list-off violations, preferably into one place, so it makes it easier on the subclasser. That way the subclasser had to add one extra method as an adapter to the parent class, so it gets all the parent work for free. Okay. Circle ellipse problem. How many of you have heard of it before? Okay, that's fantastic. So I'm going to make a circle and I'm going to make an ellipse. Which one should be the parent class? Ellipse. Of course, the ellipse is the parent class because it's more general, right? A circle is a specialization of ellipse. That makes perfect sense, right? Except that my ellipse has a method on it called skew. And what skew will do is multiply the x-axis length by 2 and the y-axis, the minor axis, by 1/2, keeping the area the same. So now circle inherits the skew method. What's going to happen? We've got a problem because if skew gets called on circle, it's no longer a circle anymore. So obviously, ellipse can't be at the top. So I think all of you guys were wrong. We'll put circle at the top because everybody knows that ellipses are just circles viewed from an angle. So here's a circle, and then I start to tilt it, and it starts to become... So I've added on a view angle, and that is a perfectly good way to... But circles have this unique property. The bounding box for a circle is a square. And so you can rely on that, and I'm sure lots of client code does rely on it. I'll take one side, and that tells me the side of the bounding box. So if I now put in an ellipse subclass where that is no longer true, I've violated an invariant of the class. In other words, there is no right answer to official technical right answer, Liskov-wise, as to which is in charge, the circle or the class. Any of you who gravitated right away to circle or gravitated right away to ellipse, you were wrong. Because that is not the principle that you were using to get to that had a violation associated with it of some invariant that was broken depending on your choice. So how do you decide which one should be on top? There is no principle of specialization because you were taught that subclasses specialize the parent. Throw that out of the window. That's Java and C++ thinking. A better way of thinking is, I've already given you the hint. Why do we subclass? It's just a way to reuse code in the parent. So the way you choose which one should be the parent class is that which has the most code that's reusable by the other class should be the parent. Amen. Thank you. So the principle for deciding which is the parent class is that which maximizes code reuse. Throw notions of specialization out the window. A dog is a special case of an animal. It turns out if your dog has a lot of functions that are reusable by animal and not vice versa, put the dog on top. Okay. All right, who learned something new? Okay, so the lessons that we learned here is that taxonomy hierarchies don't map neatly into useful class hierarchies. Every time somebody goes down this path of mapping a taxonomy, something bad happens to them along the way. For instance, we get this bright idea that we can take our exceptions and organize them into a tree. And then people come along occasionally and say, I want to make the tree deeper and specialize all of these things. And they get into a problem because sometimes you get an exception that really... It's kind of a value error, it's kind of a type error, it's kind of a runtime error, and you have to decide which one of those that you subclass from. What's the right answer, by the way, for how to do that? You can inherit from all three of them. That way, any client code that is catching runtime error, value error, or type error will match the subclass. So you use multiple inheritance on that. How are you supposed to know such things? You do follow my Twitter stream, right? Raymond H. So I don't tweet where I'm standing at the moment or when I get off the airplane. My challenge to myself is to do technical tweets in 140 characters or less and to not waste your time. So several times a week I emit technical tweets and I tell you things like, hey, this is the way we solve the problem in the decimal class where when you raise a subnormal exception, it represents several other decimal type of exceptions also because the flags and signals are all interrelated. The taxonomy doesn't map neatly onto a class hierarchy. You need to throw that thinking out. Anytime you see a taxonomy and say, oh, animal, dog, snake, cat, throw that thinking out. Think strictly in terms of maximizing code reuse and do multiple inheritance if necessary in order to violate the taxonomy. Substitutability is not a non-trivial problem. Don't think, if you think of it as a trivial problem, oh, well, you just. If you start your sentence, well, you just, when one of your junior programmers asks you a classing question, if you start off with, well, you just, you're already giving them a wrong answer. It is a hard problem, and if you dismiss it as an easy problem, then you are not actually answering their question for real. Maximize code reuse, do multiple inheritance if necessary. Let's challenge our view of subclasses as a form of specialization and think in terms of code use. This is where you get your clarity. Think about code reuse. How long have I got? 5 minutes for the open-close principle? You must be kidding me. Software entities should be open for extension, closed for modification. I forgot whether this came from Clay Gorman or Uncle Bob Martin. You guys should all follow Uncle Bob Martin on Twitter, by the way. His tweets are also excellent. This idea has multiple interpretations. It's interpreted differently in the Java world. In the Java world, it's used as a justification for using an abstract base class for everything and specializing. But there is another view, a more modern view, which says objects have internal invariants, and subclasses, the job of a subclass is to not break those invariants. So you can extend classes, add capabilities, but your idea is you don't want to break your parent class along the way. So software should be designed to be open to be extended, but closed for modification. The underlying part should still work. Let me show you an example in the standard library. We want to inherit from a dictionary. Dictionaries were designed with the open-close principle in mind. So I want to make a case-insensitive dict. Who's ever written code like this? You override a set item and override get item. Get item does a lowercase key, and set item does a lowercase key. Anybody written code like that? Was anybody not, and then it started to work, you stored Django with mixed case, you looked it up with another funky case, it found it, but look at this. I do a dget, and it says not found. How come it worked here and not here? And turned out overriding get item was not sufficient to override get. So get bypassed your extension of get item. Who is not amused by this and is angry? That Guido, we'll get him. Angry villagers with pitchforks. He did it for a reason. Dictionaries have invariants, and it's possible for you to do something that broke its invariants here. And if get were relying on get item having done something, and your get item didn't do it, it could break it. What's the consequence of breaking something that where C code is expecting an invariant? Segfault, blue screen of death. We try and guarantee that doesn't happen in the normal course of Python usage. So this was designed with the open-close principle in mind. A fact of life when subclassing built-ins is that you need to override every method as opposed to override one and expect all of the others to follow in suit. That way we don't break the internal invariants. If we do that in C, how can you do it in pure Python? There's a mechanism. Who knows what it is? There are 2 underscores. Here's what the underscores are actually for. So this is code that similar to something that I used in collections ordered dict. So init can take an iterable argument in a dictionary. The iterable argument is a list of key value pairs. So that will populate the dictionary. We have another method that does something very similar. That's update, which also takes an iterable and updates the key value pairs. So that we can have our code factored, I'd like to have init call update. So that makes sense. So I could have just put self.update. My problem is if a subclasser came along and override update, let's say like collections counter overrides update because it has a completely different signature. Collections counter would have broken init, which would have been entirely unexpected for counter. We would have made life tough for a subclasser. When a subclasser overrides update, they expect to just be able to override update and not break the whole rest of the class. So the technique is to call self under update and then map under update to update. What does that do? We have 2 pointers to this method definition. So there are 2 names of this class, or update and under update. When this one calls under update, that's guaranteed to not be overridden by any other class. The under does name mangling in order to prevent subclasses from stomping on it. We've actually made life easier on subclasses by hiding an internal call and saying, I am expecting that when I call update, I get exactly this one, and that the subclasser is free to change update without breaking my init. Who learned something new? That's what the double underscore is for. I had to trace back and find the original justification for it being there, and that was the argument for putting it in. It has nothing to do with public and private keywords, and because Python is a consenting adult's language. We don't lock the door, we take our tie and put it on the door and say the room is occupied. All right. If you go in, what you see and how you react to it is your own problem. All right, guys. I have been informed that I am about out of time. Matthew, that was for you. Thank you for coming, guys, and welcome to this huge, wonderful Pycon.